Okay, so today we learn an important definition called a linear combination of vectors. So this is phrased slightly differently from the way that it's phrased in the book, but it's equivalent. And this is the sort of format that we see more commonly in problems. We'll say that a vector W is a linear combination of the vectors v1 through vn if we can write W as a weighted sum of the vectors v1 through vn. So what that means is we're going to take the vector v1, we might scale it by some value. So make it longer or shorter, maybe switch the direction it's moving in. Same thing with v2 through vn. So if we can express W as a sum of these vectors v1 through vn, where we adjust the lengths of the vectors v1 through vn, then W is a linear combination of these vectors. Okay. Next, let's take a look at an example of trying to decide whether or not a vector is a linear combination of a pair of vectors. We could also do this for a triple of vectors or 4 vectors, 1 vector. But we're just going to start with just these 2. And we're going to see a connection between a question of a vector being a linear combination of a set of vectors with a system of linear equations. So let's take a look at this example. So we have the vector 1, 4, 14, and we have these, we want to know whether or not this is a linear combination of these vectors v1 and v2. Okay, so what we would like to know is if v1, if rather v is equal to c1 v1 plus c2 v2, where c1 and c2 are unknown real numbers. Okay, and let's write in what these vectors are. We have 1, 4, 14. v1 is 1, 2, 3. And v2 is -3, -4, 2. Okay, so the vector, we want to know if the vector on the left can be written as the sum on the right-hand side. Let's combine this right-hand side a little bit more. So if we wanted to scalar multiply the vector 1, 2, 3 by the number c1, what we're going to do is multiply each term in the vector by c1. So that's going to look like 1 times c1 plus 2 times c1 plus 3 times c1. If we wanted to multiply in the vector c2 to the second vector, so we wanted to scale the vector -3, -4, 2 by this factor c2, we're going to multiply each term by c2. So we get -3c2, -4c2, and 2c2. And now we're able to term by term add these vectors together. And so we have c1 minus 3c2, 2c1 minus 4c2, and 3c1 plus 2c2. We want to know if this equality holds. So if these vectors are going to be equal, that means that their first entries have to be equal. So we want to know whether the vector v is equal to this this sum of vectors on the right-hand side. To question equality, we need to know that the first entries are equal. So 1 equals c1 minus 3c2. We need to know that the second entries match. So 4 equals 2c1 minus 4c2. And that the third entries match as well. 14 is equal to 3c1 plus 2c2. And if we can find c1 and c2 that make each of these 3 equalities hold, then indeed V is going to be a linear combination of V1 and V2. Notice this is a system of linear equations. So we know how to solve this. Let's solve it. We're going to build an augmented matrix. So my first column is going to be coefficients of C1, then my second column will be coefficients of C2, and then my third column is going to be the augment, this vector 1, 4, 14. So we have 1, -3, 2, -4, 3, 2. Our first equation was 1C1 minus 3C2 is equal to 1. My second equation is 2C1 minus 4C2 equals 4. And my third equation was 3C1 plus 2C2 equals 14. We're going to row reduce. So we start at our pivot here. We're going to replace row 2 with row 2 minus 2 row 1. And we get 0, -4 plus 6 gives us 2, and then 4 minus 2 gives us 2. Okay. We want to clear out the 3 below the 1, so we're going to replace row 3 with row 3 minus 3 row 1. You can always do this out on the side. Maybe we'll do that in this case. So we had row 3 minus 3 row 1. So our row 3 was 3, 2, 14. And we're subtracting away 3 times row 1. So that'll be 3, -9, and 3. Subtracting these guys, we have 2 minus -9 gives us 11. 4 minus 3 gives us 11. And then 3 minus 3 is 0. Okay, and we see that we have cleared out the values below 1. So we move down to the next row and look at its leading term. Notice we can divide row 2 by 2. And so we have 1, -3, 1, 0, 1, 1, 0, 11, 11. And subtracting 11 copies of row 2 from row 3, we see we'll have a row of all zeros. Okay, so let's do that now. We're replacing row 3 with row 3 minus 11, row 2. Okay, now we're not quite in reduced row echelon form, almost there. We have our pivots moving down and to the right. Now we're ready for the upward phase. We want to get rid of this -3. Okay. The way that we'll do that is by adding 3 copies of row 2 to row 1. Okay. And so this gives us 1, 0. So we had 3 copies, so we've got 1, 0, 4, 0, 1, 1, 0, 0, 0. Okay, and now we're ready to interpret our results. We can read this off as a set of three equations. C1 equals 4, C2 equals 1, and 0 equals 0. So V can be written as 4 times V1 plus 1 times V2. What we've found is that these, when we add together the right-hand side, it produces a system of equations that we want to solve to find these unknown weights, C1 through C2. Okay. All right.